cannot get this to actually get everyone of it, so
accurately capture the so I think that let's hang up on there's all this push yeah, there's a certain amount of is it you'd like to believe that also I go back to the question why is it really about
but you're not getting confidence. You're not facing at all.
Let's get the argument maybe they don't have lined up. It seems to be rather easy. So what you use
exactly. One well, we can connect four simultaneously, so we can have four beams going on. And so you have to very carefully focus each one of these at one of these. Right, so one of our motivations will be have a mission that corresponds to one of the 16 beams that we can't activate. So we have to kind of sweep through and see which one has a message. I mean, what frequency is it? 28. So currently it's sitting as their receiver.
I sent a lot of
right now it's receiving.
I didn't make about it was cool.
So you have to carefully machine this so that all these signals are focused at the right part. Right. So you machine this whole.
Well, we can do it. We fortunate we can do it last time.
So this is something who's built this. This is also a piece
we designed it.
Oh, okay. That's right. And this signal coming out here, that's a 1628 gigahertz signal.
Yes.
Oh, I see. Okay. And then
the switches. And so we have 4 RF tunes, which are all these, and there are 4.
I see.
Each RF tune is going to switch to one of these 4. And then
oh yeah, there it's coming in.
Going back, and there is this is a multi-user or single user. Okay, so this is a single user. Which one is running?
So the interesting thing is that this damn thing is just tailor-made for 48 gigahertz. What is that?
Can you tell me how does that relate to wavelength? 28 gigabytes? That's about half of it. This is a mirror. This whole place is fortuitous for 28 gigabytes. You can get non-line sight. So
I see. So this is analog IQ, and then
this is digital IQ.
This is digital IQ.
From the FPG.
Then you have a chip.
This is a VGA. This is receiving. And these are 4 channels. So we have 4 RF chains and data streams. And then we can switch between them. And what this is showing is the 16 channels on which you can.
So this is digital IQ, and then where's the down conversion?
Down conversion is right here.
Oh, and that also has the A to D converted. And then,
ADs are in there.
oh, that's what, so this is analog.
No, yeah, this is analog. You're right. Sorry, I stand correct. This is baseband. Analog baseband. Exactly.
Yeah. Okay. So the analog baseband, and then it comes into.
Here it gets up and goes straight up.
I see. Very nice. And then you have those are switchers.
And there are 1 to 4 switches right now. That's a simple thing.
Very nice.
And so so what that red stuff is showing is that people are drunk. So, those are the stronger beats. So we choose 4 out of these 16. We're showing all of them. And if I move that right now, right, somebody who Kevin, go and move that puppy. And it will shift. But I think we should shift it to the multi. Okay. Which one is that one? Okay, slow down. No, don't line it up.
And that's just a horn antenna.
That's not even a horn. That's a waveguide.
I can't even see it. Okay, that's just
so the strong one. I mean, there's all sorts of reflections going on right now. But it's showing you which one of the 4 strong beams. And so we can decode. Is this everything equalization running too, right?
Yeah.
Okay. So I think now we should use it. Yeah, but anyway, we should put on-line side later on. But how about we run? So move this way.
Just
move this way. More. Very good. Oh,
no, it's taking 16 of them. Each beam is that. But if you start
so you can look at that, the 4 strong beams have shifted.
Right.
So it's going this way as it shifts. So what this is showing is that it is tracking. It's in fact the beam width here is about 4 degrees, and this is equivalent to guess what's the equivalent size of a phase array. How many antenna elements have wavelength? It's 6 inches. So it's about 700 elements. So nobody has built that. So we have a very high gain, very narrow beam, and so rather than steering it, we select it. Right now we just have 16. We can make it bigger, and I think this to me is absolute viable for access points. So yeah,
fit that.
yeah. I mean, this would be right now. This is not going to be waveforms, man. This could be patch antenna right behind it. We can even optimize this part. This could be an RF board right in the back that we're actually going to do, and so you can do that and actually at higher frequency. So, and then we have a multi-user station too, and that'll be actually very interesting where you see the two. And you can see that, the temporal equalization, we have very close multi-beam, almost similar I want to use that too. Should we switch to multi? Let's just switch to multi. Yeah, actually, wait. No, so we have 4 RF chains, 4 data streams, and we map one, in this simple case, one to each one of these 4. So we have 16 possible, and each quadrant, one data stream, and we selected whichever is the strongest. So we took the strongest out of each quadrant and used those. And for multi-users too, we have 2 users, but we select just 4 strongest beats. So there's a beat section going on. But we are displaying all the 16 beats. No feedback. It's just transferred out. We select it. We actually have a whole thing which tells you this is your channel estimate for this is the estimate of beams, so it's the whole shebang. That's a transfer. responds to all the 64. Constant scanning.
Okay, so
Okay, something is.
I think we switched to multi.
Okay. So what they're showing is all the 16 feed signals because it's scanning and showing them, and then we show the red one used for decoding. And here, right? One interesting thing is we have a frequency sync implemented too. So those oscillators pretty damn simple. You don't even need to calculate frequency oscillators. It is surprising. It really is surprising. That was not the case at 10 gigahertz. That's not fair. Frames, yes. So what is your ADC system?
Yeah.
Much faster than and then you have these oscillators, and so you said microseconds. How many microseconds? Microseconds. Okay, 126 microseconds means that if you have, say, a nanosecond of sampling time, so that's like a lot. So that includes data. Okay, so maybe also, so where do you use it?
So what I'm saying is like you got a point. So you have this quantity is broken up into what summarize your point. So you use that
Use one pilot for the entire one.
One of the 16 antennas, the lens focuses.
I think we will aim from an NB here. We're going to do I want to see how far, I want to see tracking.
Yeah, so we select the feed based off of where the transmitter is located. So one feed corresponds to one feed because the antenna as opposed to a phase array where you have to use all.
Oh yeah, I think, yes.
Right.
Now there is so this is now for
simplifies the RF.
Hey, so what is this? What is running? Multi-user, or what's the processing? Oh, this is multi-user processing.
Yeah.
So right now you can see they're very close, and there's still some glitches sometimes that happen that we are not decoding, but every once in a while you will see the constellation. How about let's step back and separate them a little bit. Well, actually that's not bad. But so this is what it's doing, is doing spatial and temporal processing, and this is showing is the beams that are selecting for the two users. So you can actually see that their directionality is reflected in the strong beams that are being used for the two users. And now if you move it, hey, tell them, move them closer. And mess it up. But we can actually hold them very, very close. And this is simultaneously both users are being decoded at the same time, and we're doing everything, channel estimation. Very cool one. How long? Hey, Chris, how long is our frame? What's the number of samples? 16,000 sample, and then we are similar to 370, so we should know what's the length in microsecond. 370 is like 0.3 nanosecond, or 3 nanoseconds. 3 nanoseconds times 16,000. So that's like 50,000 nanoseconds, 50 microseconds. Hey, that's not that much long. That's about half of what you're talking about. Oh, yeah, that is.
What's your oscillator?
Well, it's a connectorized one. That's why I was saying, what is your oscillator? What is your RF?
The number I use is just
This is picking up 2 beats.
Hey, come on, man. You're safe. There's no microphones here. Hey, these under the radar companies. Why do our companies sit at their hands off? What are you afraid of? Come on.
I'm just a movie for some.
Oh, yeah, that's what we all say. I hate that expression. Yeah. And I'm the goddamn general, damn it. So you gotta listen to me.
Exactly. We do.
Oh, yeah, we want to replicate it, so it's about, that's about 5K, that's about 15K right there, that's the most expensive part. And then we want to get the R board integrated a little cheap, so we're going to get that. And then the other user, right now I'm making over there. So, okay, so what's the... Yeah, so let's do... Yeah, we should have laser beams there, but if anyone definitely try it, so you see, right now it's very tricky. You can still decode it and see how close they are.
1.5 feet.
1.5 feet, and that's within a fraction of a beam. So it's within the beam width, so we can still decode them. You can see the constellation, and if they're separated, it is even prettier.
That would just be there.
Yeah, somebody better be there. Hey, no, you have to pay to touch. Four data streams, 16 feet. We select, we scan. That's what you. Well, right now we're not showing because we are doing all the things, but we can show all 16 of them, and then you process them 4 degrees. And this is equivalent to a 700 phase.
Akbar, can you tell me more about this?
This is Rexolite lens. It's literally like a convex lens made with plastic. It's really cheap and it has a flat dielectric constant from about 50 megahertz to 500 gigahertz. So it's beautiful. So it's just a lens and it's very cheap. And then we can, right now we're using feed antennas for our, not even feed, waveguides for our feed antennas, which could be better. And we could even change the focal length, optimize that as well. And we want to integrate, all of this could be integrated into one RF. Okay, and that could literally be right behind it. Because these are evaluation boards from ADI. That's the chip. These are connectorized. So they all would be, and the brain, the digital baseband unit is right there. There's an FPGA, BC707, and then 2 DAC ADC cards, which support 4 complex channels at 370 megasamples per second.
270 megasamples.
370 megasamples. So we're going to upgrade that too, and then what we have right now is, this is actually interesting. We're getting the data over the Ethernet port, and we are processing it in MATLAB and displaying. So it's subsampling it, and soon we'll have a real-time processing right on the FPGA. That's what we're working on right now. And I really want to get stable versions of these access points on the power platform and to other academics too. So that, but the thing is, this is completely from scratch. You can control every goddamn thing in there. I can observe everything in here. There's nothing under the hood. Everything is discrete here. This is a VGA, this is a mixer, this is the oscillator, those are the LNAs, and these are the switches. 28 gigahertz.
Do you plan to put some data link on top and do some higher layer.
Absolutely.
Like,
Yes. Yes.
and push a video or
So
something.
so as part of our project, yeah, absolutely. So our goal is that we'll have a network of 4 of these at the end of this project in the next 2 or 3 years, and then 2 UEs, and we want to be able to communicate from the UEs through our network, access the internet or whatever, and then download a movie or something over the network. And we absolutely want to have the skeletal stuff in there on our FPGA or MATLAB to actually play with the 5 Mac and higher protocol. So yes, we should talk. I want all the input we can get to, and this could be related to emulation stuff too that you've been talking about. So I think, and then this is a channel measurement tool. Absolutely state of the art. Nobody can measure channels like this simultaneously at this resolution right now. Nobody. Period. Nobody can do simultaneous. We can measure simultaneous 4 beams. Nobody right now can do that. They all have their separate patch antennas and each separate phase arrays to be able to do that. And those phase arrays don't have anywhere close to the speed.
But how about am I able to capture the whole 180?
Yeah, so what we need to do is, what we can do is put more feeds, and it's a question of scanning them. So in your case, you change the phase shifting weights to scan. Here what we'll do is we'll switch across different ones. So just imagine if you had multiple one of these, you can easily imagine feed array. It doesn't have to be 16. I could easily replicate 16, 16, 16 all over. And then I could have more switches. I'll have some more loss, but I could map, or I could add more RF chains. Look, our cost is so much little that, you get an estimate from NI, and even they start getting sheepish that, I'm really sorry, the numbers are getting tight with 4 beams, and we can get more RF chains because cost is, it's not going to kill you. Yeah, it is, it's crazy the amount of bullshit
So you have
going
some
on.
modular. You can
It's
put
modular,
together.
absolutely. We can do modular, and yeah, we are developing our own FPGA, and I am very hopeful, and I think we may be clever with NI or MathWorks, we're talking to them too, to be able to develop. Do you know that you can actually develop HDL code out from MATLAB?
I was very surprised to see. In fact, I wanted to ask you. I see MATLAB there.
This is MATLAB. But by the way, this is processing happening outside. This is actually happening in MATLAB. So we actually write a code where it just gets the data off the FPGA, and it's actually processing in MATLAB. And you're just seeing a subsample version. Ultimately, we're going to push all that data in there. But the interesting thing is that if you build a system in Simulink, and I think now you can even do it with MATLAB, you can build it and you can actually generate an HDL code that will get transformed. Because HDL code is a pain in the ass. But, there's still kinks there. So that is a big time sink. But I think we have learned a lot, but it's exciting. So I think between channel modeling, emulation, hardware in the loop and stuff, and sound like this, just
Down convert from the 28 gigahertz to what frequency? Baseband. Which is how many years ago?
It's a duct tape.
Oh yeah, duct tape. Well, this is a very stable version, my friend. You should have seen the last one, where if you sneeze, it'll stop working. But I made the NI one work. I touched it and it stopped working. Very fragile. They're delicate.
So if
Delicate $300,000 equipment.
So if you use MATLAB to do all these processing, can you run that fast?
Yeah, this is subsampling. So we want to push all that code into the FPGA.
Right.
But right now we haven't gotten to that point.
Right, yeah.
So we are just getting the data out,
Okay.
and we are just real-time subsample. You're just seeing obviously, frame by frame subsample version.
So these 4 streams share these 16 antennas?
4 streams.
You
share
mentioned
the 16
there's
yes.
Yeah. Okay.
Yeah. So what do you select?
Okay.
One out of where's the camera?
Oh, it's right there.
Oh, okay, very good. So we are streaming.
Yeah, and
you can check it.
You can hear yourself talk.
All right. No, I don't like to do that.
We're sending
Very good. Very good. Excellent. Good job. This is a bootstrap operation. I'm so proud of my team. Look at that.
That's a really nice.
yeah, we're working on that.
So what you do is first thing say the D or something?
We're using a 40
Bursky? What do you mean bursky?
with a TI chip on it.
And where is that?
That's all down here. So we have the ADC, and then through FMC cards to WJ, Xilinx WJ.
And then is it an Ethernet to get into there?
Yeah.
And so then you're not doing anything on the DSP board, it's all just being burst transferred into the PC.
Not at the moment. Eventually it will be all onboard processed.
And so really nice. Algorithms are all written in MATLAB.
They have this Dynamo system.
They're writing, you know, you could write them in Java.
Yeah, is that better?
Well, it's not you know that MATLAB is Java in reality.
Because I've been playing around with like object-oriented MATLAB programming. It's a little weird compared to Java.
No, MATLAB is Java.
Yeah.
Because the figure windows and the command window are JPEGs. That MATLAB some while ago is big honking Java, which then goes across the native interface for the vast library of Fortran and C programming. You knew that, right? Now you do.
So I guess what's the advantage of using Java over MATLAB with all the built-in functions already?
Well, if you're using the built-in functions, that's fine. You're using software. But if you need to implement some custom algorithm, Java might be more powerful and flexible because they I don't know if they have a similar thing to Java of an incremental translator, but unless you're using block routines like FFTs or singular variable composition or whatever, just doing loops in MATLAB is very slow. It's all interpreted unless they change something. Whereas Java is interpreted, and so loops in Java are also slow, but if you're running lots of them, they are incrementally translated. And that if you warm up a Java virtual machine, it can be as fast doing loops as C. Okay. Scout's on.
Provided you have enough memory to play with.
Well, if you're programming in Java, you just don't allocate, you don't create objects willy-nilly. You cache your objects, so you create them once and then your arrays or other objects containing arrays. You don't allocate them and dereference them.
I've seen, I mean, this is not about this in lot anymore, but I've read articles where they talk about how garbage collector performance just drops off a hill after you hit a certain percentage of memory usage. Java garbage collects.
No, you don't. If you're writing a Java app for this purpose, you create a structure, you allocate all your structures or objects or arrays, and you don't release them.
So you define one object variable and then you just keep updating the elements of that object,
right,
instead of defining a new one each time.
Yeah. And so the other thing is, if you write these algorithms in Java, they're kind of in a form where they're more easily translatable into C. And in Java, from the MATLAB command window, you can create instances of Java objects and invoke methods on it.
I think I've read about that, yeah.
So the Java command window is essentially the MATLAB command window is essentially a Java shell.
Some interesting toolboxes out there that allow you to compile code down to C from a MATLAB script.
Yeah.
I mean, it's not very clean, but you can try to wring some performance out that way. for prototyping.
Yes, but think about what I have suggested. I'm not saying you have to do it. It's just an option. Well, thanks for presenting.
Yeah. Good talking to you.
Do you want the mic?
What? Are you able to hear yourself?
Yes. It's on a delay, but you should wear it 'cause you're going to be next to the camera and you're going to be talking. So.
Okay. How's it going?
Good. How are you? This is your project?
Yeah.
Can you briefly introduce me?
Yeah, so we have a transmitter over there, and we're operating at 28 gigahertz. The lens focuses the transmitted signal from a specific direction to a specific antenna feed.
Yeah.
So we just select one of the antennas for a given direction, instead of a phased array where you have to kind of use all the antennas.
Okay.
And then, so we can activate 4 antennas and 4 beams simultaneously. VGAs, they're amplifiers. Yeah.
Baseband amplifier or RF?
Baseband.
You said the RF amplifier?
That's the IQ mixer. And then we have the LNA, which is passband amplifier.
And this is the analog beamforming, right?
Yeah, we're using the lens to form the
If
beams.
it's analog, do you have any phase shifter to change the phase?
No, it's all done by the lens. We're able to get 4-degree beam widths.
So I'm trying to understand. If you move one of the transmitter to the side,
Yeah.
right?
Yeah.
So how would this perform a beam
So,
with that lens?
so if the transmit antenna is like over here, then to activate that beam, we just have to be reading on this antenna feed,
Right.
or one antenna feed corresponds to one beam,
Right.
and then that goes through its own RF chain. And since we have 4 RF chains, we can activate 4 beams simultaneously.
Oh, I see.
And we have all kinds of switching to switch between the beams.
And you're not using any phase shifter or
Right.
changing phase or any of those parts.
Correct.
I see. Gosh, thank you.
Correspond to a single
Wonderful.
Yeah.
Anybody would be kind enough to tell me more?
Sure. So we have 2 transmitters on that end, and the lens focuses the transmit signal to a specific antenna based on which beam it's
I know
on.
you have a patch. I can't see very well.
What?
It's a patch antenna or it's a single?
It's a waveguide antenna.
Okay, so it's a single element.
Yeah. And here we have a 4x4 antenna array. So to activate one beam, we only need one antenna. And then because the lens does the beam forming, we get 4-degree beam widths with the lens. And then fixed.
Can you change the beamforming? I mean, is this controllable?
So, I mean, we can mechanically.
Yes, so it's
but
fixed.
other than that, yes. Yeah, and yeah, so if we want to activate different sections, we just activate a different beam instead of mechanically steering anything.
Yeah.
And then each beam has its own RF chain. Currently we have 4 RF chains, so we can activate 4 beams simultaneously. And
So you have then
we have switches.
hybrid, so it's a 16, a factor of 4 between RF chains and
Yeah.
so 4 elements are
4 elements are selected at the same time. And we use the RF switches to select, to control which ones we're selecting, and then they go to the RF chains, and then do the ADCs and processing.
you use it as a channel sampler or
Currently, we're transmitting our own test frame, and then we're able to decode from each of the mobile stations simultaneously. So on the left is mobile station 1, and on the right is mobile station 2. That's just showing the constellations. And then all the way on the right, we're showing which beams we're selecting.
so are they more than 4 degrees spatially separated?
Not currently.
It looks like they're parallel.
Yeah, so they're pretty close right now, which it's impressive that we're still usually able to decode.
Sometimes different. You see, I see them.
Yeah, I think there's a lot of multipath in this lobby area, but usually they're close to the middle 4 antenna feeds.
So is it angles? What do you have here on the axes?
It's which feeds we're activating. So there's kind of 4 vertical squares and 4 horizontal squares that represent the antenna feed array.
So not always you separate them because they're very...
Right, yeah, so I think it's easier for the algorithm to decode if they're more separated, but they don't necessarily.
Angle that.
Right, so the farther away we go, they actually focus more on one single beam instead of kind of multiple beams.
If you want to get a specific kind of beamforming, I mean, mechanically, how do you have to, I mean, do you calculate on paper first and you say there has to be X? I mean, the focal point changes with frequency, you know? How do you decide this goes here, not here, this goes here?
So I think the focal point or the focal length depends on the lens.
But it would shine different antennas at different frequencies. So you go from 20 to 70, wouldn't it change?
I think so.
And what is this? And what is the battery?
It's a Rexolite. It's a high-performance plastic.
Falls under the metamaterials?
Maybe. Yeah, so it's a dielectric lens.
So if I'm blocking,
These are
Right, so now we're not getting any constellations.
amplifiers, right?
Yeah. Yeah, so it's primarily line of sight. It might take a minute to, there we go. It's kind of...
thanks for
Yeah.
How much power you're sending out?
How much what?
How much power?
I'm not sure. So that side's actually a transmitter, and we're just receiving here, but yeah.
Okay, then I'm safe.
And this is how much different from the microwave.
Yeah, it's pretty low power.
So who designed it? I don't need to say. Who designed it?
I think our lab lab designed it, and then we had it manufactured by some company. I'm not sure.
Really? We designed the manifold?
I think so. It was before I got here, so. Yeah, I heard Akbar saying earlier that we designed it, so I guess we did. Hi, how's it going?
On the reflector?
What's that?
Horn and a reflector? It's a wavelet, right?
Yeah, and then we have a lens. So
that's a lens?
Yeah.
Okay. So signal comes out.
So currently, this is the receiver, and we're transmitting from over there. So the signal is actually being focused by the lens to one individual feed, and then so we're able to, with just the lens, we're able to get 4-degree beam width, and each feed corresponds to a different beam. And then we do selecting. We can select 4 beams simultaneously because we have 4 RF chains behind it. We use RF switches.
So these are waveguides, right?
Yeah.
We were hitting between 1 degree with a maximum gain and a larger amount of degrees with a lower gain. So why did you go to 4-degree beam width? Is there any reason specific for that?
Not that I know of.
So they all like pointing towards the center of the lens.
Yeah.
And this is convex. Convex, right?
I think so, yeah.
So when it comes out, so this is for increasing the gain.
Yeah.
No, it's making the wave planar, like the plane wave. Yeah, instead of like normally when the wave so what is collimating the beam? Are you collimating the beam? Right?
Yeah, I think so. But it focuses the beam, so we also get a higher gain at the one antenna that we want to be.
So you're only using one at a time?
We can activate 4, but one feed corresponds to 1 beam.
Okay.
So we can do multi-beam forming.
Did you measure gain? Did you measure gain? Antennas?
Yeah, so with or without the lens gives us, I think, 11 dB of gain, about. So it's fairly good at focusing the incoming signals.
What's the baseband processor board? Is it a WAR board? It's programmable as
Thank you. Yeah. Hi.
Can you explain?
Sure. I'm Chris. So we're transmitting from 2 mobile stations over there. The incoming signal comes through the lens to the antenna feeds. So we're doing beam forming, but it's all analog beam forming using the lens. So one antenna feed corresponds to 1 beam. And we're able to get 4-degree beam widths with the lens. And is a what?
This is a transmitter, or which one? What is the transmitter receiver?
This is the receiver.
Okay.
That's the transmitter. Yeah. And so we have 4 RF chains, so we're able to activate 4 beams simultaneously. And yeah, so here we're demonstrating decoding from 2 transmitters, and we're showing which beams we're selecting out of the 16.
And the location of the transmitter roughly corresponds to which is not. So that's how we do beam selection. And we can select 4 simultaneously. So I know we are able to
16 beams?
Yep. We have 16 beams that we can select from, and we can select 4 simultaneously. And we use RF switches to control which ones we choose. Because the number of beams corresponds to the number of antenna feeds we have.
Yeah, so you said that you have 2. Are they transmitting simultaneously?
Yeah, so we transmit a channel estimation block, each one individually, and then we do all the channel estimation, and the data blocks themselves get transmitted simultaneously. And that's what we're showing here is the data blocks decoded. It's OFDM.
Which frequency are you? Which frequency band?
So what are the different, what is the rows? What are the rows?
Yeah, so the columns are the 2 mobile stations. The rows are just showing we have multiple data blocks, so multiple OFDM symbols.
What's happening over time? You're refreshing, right?
Yeah. So it's real time, or more or less. There's some lag in it, but so if you stand in front of it, then we won't get constellations. And if we move the transmitters farther apart, we'll probably get better constellations. Right now, they're pretty close to each other.
Okay, so now it's very bad, right?
Right, he was putting his hand in front of it.
See, because the processing is actually going through that.
There we go. Thank you. Yeah. Hi, how's it going?
Can you explain what is it the lens, right?
Right. Yeah, so
Go ahead. Oh, yeah.
And all these things have the antennas for you.
yeah, so we have a 16 feet antenna array. Each antenna corresponds to a 4-degree beam.
4 degree, okay.
So we only need 1 antenna to form 1 beam, and we can select 4 antennas simultaneously, so we can have 4 beams that we're receiving on at the same time, because we have 4 RF chains. And then, yeah. Yeah, so this is a RF switch that we use to select each one.
So the other side is also the same setup or what? Or is it different?
Say that again?
Is that the other side? You have the same setup over there, or?
Yeah, so the transmitter's over there.
Yeah.
We have 2 transmitters that we're sending information on.
This one?
Yeah. What was?
So is this a transmitter or receiver?
This is a receiver. We got 2 transmitters on that end.
Comes down to
Yeah, so we have 4 RF chains.
This is the baseband.
Right, these are baseband amplifiers. This is where it gets converted down to baseband at the IQ mixer. And then it goes to the ADCs. And
How much bandwidth are you
370 megahertz. Yeah.
So your sensor FPGA is working at least 370.
So how do sampling? The samples come in at so how do they get the FPGA? Yeah, how to obtain credits? What do they do to get the credits?
Characterizing,
exams and labs, you get some credits. And,
do you want to use this as a measurement platform?
Yeah, we plan to do like channel measurements and stuff like that with it.
Have you done any channel measurements? Have you done any, or you want to?
I think we have in the past.
If you have enough of applications.
Almost time for lunch. Hi. Yeah. So we have a demo, but these people blogging is mostly line of sight. But our transmitters over there, and our and our receivers here. We're using a lens to do the beam forming. So each antenna corresponds to one beam, and it's 4-degree beam width. And we can select 4 beams simultaneously because we have 4 RF chains.
Right.
And then we do all our processing from those 4 beams. We're able to decode 2 mobile stations simultaneously. So
28 gigahertz.
So then,
Did you get the right from
the maximum bandwidth, how much it is? The throughput.
So we have the bandwidth of our system is 370 megahertz.
For each antenna or total? The whole system?
Oh, you are not counting.
You ask Professor Saeed over there, he would probably.
Yeah, just wondering. It's allowed to use or just like indoor, that's why.
We've mostly used it indoor line of sight and over short distances.
So then how many receivers theoretically can be supported simultaneously based on this setup?
So it's limited by the number of beams that we can simultaneously select. So currently 4. And then each receiver would have its own beam.
Do they need to do some calibration or beam tracking first?
Yeah, so the first step is we sweep through all of the 16 feeds on the array and see which ones are receiving the highest power for each mobile station. And then based on that, we select 4 of them and then do all our processing.
Like the 4 users, they will, each user will only select 4 beams. Is that what you mean?
Each user will get 1 beam.
Get 1 beam.
Yeah.
But we are from 4 antennas. So you mentioned you have like 64 antennas.
No, there'd be a 16 feet array where we would select four arrays from the 16.
Oh, I see. Got it.
Yeah.
Misunderstood. Sorry. Thank you.
Yeah.
So what is this guy doing for you? Just focusing?
It's focusing it. So the beam width is smaller than it's on one antenna at a time. So
Is that the first poster is yours, guys? The same one?
We do have a poster over there.
Where is it? We don't have it?
We do. I don't know where he is.
First one.
So then I think I should need to be some escape.
Is it live?
Yep. other people standing in front of it, so.
What we are demonstrating is this is our receiving access point receiver, and those are two transmitters, so it's a multi-user setup. And what we have is hybrid beamforming. So this is a lens that forms beams, and we have a 16 feed array. And what we have is 4 RF chains and data streams. And what we do is, no, don't lean against it, please. Sit on a chair if you're tired. We have 4 RF chains, and each data stream can be switched to one of the 4 in each quadrant. So it's like, think of a 16 by 16 grid. And then what we have is, this is the RF switches. This is at 28 gigahertz. And then we have mixers, LNAs, and then VGAs. This is analog baseband, and then there's FPGAs and DACs and ADCs. And what we do, and we have a whole frame. So what we're doing is, we are decoding the signals of the 2 users. There's people in front of it, so you can see the constellation.
And this is how you will also deploy 5G, right? You have some people go and say, please move. Because now we want to don't stand in the way.
We'll get to the point where we're reflecting over there. It might be interesting. Actually, we should do it. So, so there's, you can see the 2 constellations.
Stand in front of him so we can hear him. Get the microphone.
So mobile station 1 is, which one is mobile station 1? Kevin, which one is 1? That one. So this is mobile station 1 beams, this is mobile station 2 beams that we are selecting dynamically based on their signal strength. We just take those signals out of those 16 and process them, digitize them and process them out of the 16 possible. But this sucker can actually generate 600 beams over the entire hemisphere. This is equivalent, if you were to build a phase array, this will have about 700 elements. So nobody is building it. This is a lens, so we have a continuous aperture here and a sample in the back end. So we directly measure in the beam space.
And you said something about spatial interference cancellation.
So processing, not this, we do that digitally. So this is literally, all it's doing is that it's forming beams. It's just focusing the beams. So imagine this is a 16 4x4 grid. Yeah. So you imagine a projection screen in front where there are four grid squares, each with 4-degree width. And if you expand it more, we haven't done it, you can cover a bigger area, all the way up to 60 degrees. And so, at least. And so we can do that, and we can, so rather than phase arrays or horn antennas, we can switch between these antennas and make measurements or communicate. Yeah. Yeah, yes. That's all right. It's all right. They can be very close. They're awfully close to be, and they're both sharing the entire house. So we are separating.
So even though somebody's standing here?
No. They'll get blocked. But you know, this place is, I was just saying, this is metal, and if you look at those squares, they are literally happening. So this is like a mirror. This is like a microwave oven mat at 28 gigahertz. So we can play convergence of this, zoom, and just put 28 gigahertz online. We'll actually demonstrate online sites later. What modulation you use? Just one. That's one. When you're getting ready to come off, right? Okay. But this is how we want to do measurements, and I think it's really interesting to kind of put it through a ratio. I'm very interested. We can do that. We want to figure out I think that's the kind of issue that many of the people which is performance-based even once we will have.
Well, at least in your system, you have access. Many are now integrated.
This is exactly the beauty. You can access every bit of it except the FTP. But everything else, we want to integrate this eventually so that it can dashboard down there. We do this last thing. Digitizing a 360.
So you're working on this project, right?
Yeah.
So how do you choose the curvature of the lens around the corner?
How do we?
Why do people think it's
How do we achieve the curvature?
No. How do you choose that? Is that something you just buy from the Home Depot, or you actually made it and sort of designed it?
So we didn't make it. We didn't buy it from Home Depot. I think. We ordered it from somewhere. I'm not sure how much input we had into the shape of it.
Yeah.
But yeah, it'd be interesting for sure.
Don't touch it. That's what we need. Very, very high accuracy.
Let me ask him.
Yeah, that would be a good question.
You can have a very specialized light for pointing it, but you don't touch it. That's the important one. So,
very good question. So this is a small. This is going for $700. Much bigger than this is only a 16 by 4x4, right? So it only has a 16-hole game. The second thing is you don't have enough antenna gain to get. Yeah, this is a glass. And you focus more on burn with the sun, burn the insect. Okay. How do you choose the curvature? This is just a simple, this is not even optimized. It's a planar convex line with a certain focal length. There's nothing optimized. You can optimize that. So we haven't even shown you molded thing that you can get. And this is a Rexolite, which is very common. It has a constant dielectric constant from 100 megahertz to 5 gigahertz. So it's really inexpensive. So going back to your question, this is, so you cannot do this. You cannot do, you know, so if if I were to do a digital thing, right, for this much gain, I would need 700 digital beamform now, 700 RF gain and ADC. Well, you might as well have nuclear power. So you have to do hybrid. So what people are using is phase array, but they are still small. Some of the phase arrays are just this size. And only one phase beam steering. But you can only map one data stream to the other. So we can do multiple beam at the same time. This is an alternative to hybrid beam forming compared to phase array or digital beam. So this is, and it's a lot less. Absolutely. We can scan all of them. They're actually just trying to do it. Yeah, we can really play. If I have I can not the 16. Probably you can't. So if you think about this, they're being 42 by 40 degrees. Think of the square. If they are in distinctly pure gold, if they are both in the same beam, really I think there'll be some interesting issues coming up in terms of what we need to verify.
A quick question, what is the operation? What do you use? You said half a gig to 100 or?
Yeah, this is a very wide band.
Because I read on some paper, I don't know if it was a paper.
Some trams always have few cameras, trams above it. So you need one to see.
So you're going to demo in 3 sessions?
What's that?
You're going to demo for all the 3 sessions, right?
Yeah.
Is there any difference between
Oh yeah, my name is Fulan and I work with Xingyu. He's Xingyu Gang. Yeah.
Oh, okay, where is he? He's not here.
I can't see him right now. He was just here just now, and that's our platform.
So you guys are working on this?
Oh yeah, this is a software-defined radio that works on millimeter wave band. Millimeter wave software-defined radio. This is called WARP. We combine both, but based on software-defined radio. No, I think different bands. You can see the baseband signal goes from here to BBC to analog signal. Right here is
front end before ADC.
after the signal transmitted to it is already analog signal. Oh, sorry, such as the front end, and converts the baseband signal first to parallel amplify the signal out. That's how all this works. This is a receiver. This is the median receiver. After this board is baseband signal. It's going to these. This is the differential signal.
Why you have multiple cases?
That's the differential signal. IQ. Each IQ.
Oh, you don't send access points?
Yeah, they send to different cables, and that's primarily because of the design of the translator here. Alright.
I still don't know why. Yeah.
No, these are available from a company called UV.
Yeah, let's have
Yeah, some configuration files. That's right here.
software defined AI.
Yeah. So you're able to
So the main reason you did this one, there is no USRP that supports this shop. Exactly. But you did it for millimeter wave, but there is no USRP supports millimeter wave.
Oh, that's right. That's why it exists previously, but it hasn't been supported by radio. Okay.
Yeah, I know it's
That's also a
yeah, we will check what is the max they support.
Yeah.
So in your case, what is the
So